So we're going to start 1, 2 real quickly. Like I said, I just want to do the first bit here, and then I want us to do the first example, and then we'll finish it tomorrow, and you'll have time to work tomorrow. Okay? So, because I want to stay on the limit function because you guys are saying, what's a limit? So we saw in the first section how limits arise in trying to find tangent lines to a curve. That's what we found. We found a tangent line to that curve, the x squared curve. Okay? So later in this chapter, we'll see that limits also arrive at computing velocities and other rates of change. So the applied stuff we're going to get to later, kind of on the lines of some physics stuff. In fact, limits are basic to all calculus, and so this section we look at limits in general and methods for calculating them. So we begin by investigating the behavior of this function. So when x is near 3, the following table gives the following values. So as we get really close to 3, what's it getting close to? Yeah, 0.5, right? So essentially what? 1/2, right? So as we're approaching 3 on both sides, okay, just like we did earlier with 1, approaching 3 on both sides, it gets really close to 1/2. So the limit at 3 is 1/2 for this given function, okay, by doing a table. But we're not going to be building these tables every time. But I'm trying to get to the basis. So let's just go back, just what we just did before. As we approached 1 on both sides, it approached what? 2, right? So our limit at 1 was 2. Maybe this will help you, Emily. So at every spot, every curve change, like on a parabola, it changes its not its direction, but its angle, right? So every point is going to have a different point of tangency. It's not 2 everywhere. It's not going to be 3 everywhere because it gets steeper at different spots. So for example, on a parabola, so we just did 1, 1, right? What if we did 2, 4? Would that have been a steeper point of tangency, or excuse me, a steeper slope of tangency, or a like flatter? Steeper. So we had to, if it was farther, it would have been like 7 or 8 maybe. Okay? So what we're saying on this one, and this is a different picture, this is a rational expression, okay? We're saying on this one, as it approaches 3, it's going to be 1/2. So this is a flatter slope of tangency, 1/2, okay? All right, so what does that mean? Well, here's the picture. Okay, here's the picture. So the open circle at 3, 1/2 indicates the function is not defined at 3. Why is that not defined at 3? Well, if we go back, if you didn't notice, this factored. Whoops, whoa, moving pictures. Okay, if I go back, this is what that factors to. Why is 3 a problem? Yeah, I'm having a hole there. So that's why on this picture, we have a hole there. At 1? What's at 1? The asymptote. So this is where calc gets interesting, okay? Well, at least to me. We were good, okay? Why? Let's see if you can just think about it. Why is there not 2 asymptotes? Because what's that? Correct, and what does that mean? So you guys remember that, okay? Since that cancels at the bottom, your asymptote's the only one that's by itself. X minus 1 didn't cancel. The x minus 3 did, so that's where it's a point of discontinuity. It doesn't keep going. It can't keep going through that point. It's an open dot. Okay? Good. So from the table in the graph, we see that when x is close to 3, but it's still, the thing of the point is even though there's a hole there, we can take the limit to approximate about where it's at. Even though the value's not there, it's pretty much what? 1/2. It's at 1/2. Okay? So that's what it's saying here. So from the table, we see that x is close to 3 on each side. It gets really close to 0.5. In fact, it appears that if we can make the values f as close as we'd like to 0.5 by taking it close to 3, we express this by saying the limit of this function as it approaches 3 is 1/2. Yes? Right. Since there's a point of discontinuity, we want to figure out what's happening there, and it's approaching 1/2. Does that make sense? Okay. So this is how you'd write it. Limit as x is approaching 3 equals 1/2. Okay. How are we going to figure those out? The whole section we're doing now is how do you figure it out other than the table. We're just looking at a picture and a table so you understand what we're looking at. We're going to do the actual how to get it. Okay, so stay with me. We'll do an example here. Might be able to do two. Okay, so we say that we write limit as x approaches a. A is the value that you're using to essentially where you're evaluating it at, so x to 3. F of x of the limit. The limit of f of x as x approaches a equals L. So L would be 1/2 in this case. If we can make the values of f of x arbitrarily close to L as we like by taking x to be sufficiently close to a but not equal to a. So if we can't use 3, we can test stuff around 3 is what that's saying. So we can't plug 3 in. It says if your calculator says no solution or error, then you can try stuff really close to 3 and see what's happening. Okay? So you can do that. Like if you forget how to do some other stuff, you can always kind of come back to that. Okay? But we're going to teach you how to get a little bit better than that. All right, so roughly speaking, this says that the values of f of x become closer and closer to the number of L, which we're talking about. From both sides, it's getting really close to 0.5. So like, for example, this is when limits is really easy. Why is limits really easy right here? Yeah, we have a value, and do we have any restrictions? This is simply plug 5 in. That's it, because there's no problem with plugging 5 in. When you guys have to get good and adjust is when I put like an x minus 5 on the bottom on you, and you're like, okay, I have some work to do now. This is the one where you're like, thanks for the free points. Do you understand? You just plug 5 in, it'll tell you. Okay, so if I plug 5 in, it's going to be 5 squared plus 10x minus 3. Oops, not 10x. 10. Okay, 25 plus 10, 35, minus 3. The limit at 5 is 32 for this one. Okay. All right, so the next thing we're just going to talk about quickly is just the properties of limits. You'll kind of use these to help manipulate things into your advantage. Okay, so this is an example where you may not need to write all these down now. If it's in the book, you may want to print the page off, you can. But it's kind of straightforward in a sense that suppose you have your two limits, f of x and g of x, okay? So you have two separate limits. It's kind of like logarithms in a way, but logarithms have different rules, obviously. But limit of x approaches a of f of x plus g of x is the same thing as the limits separated and added. Okay, so if I just did them separately, I can do that. Okay, so if you had two functions together, you can separate them into two separate limits. Same thing for subtraction. Okay, multiplication is if you have a constant times a function, that's the same thing, and this one's very helpful. Okay, that's the same thing as the constant out in front of the limit. So you can go and pull the constant out and then do the limit. So like, for example, we got 2. We could times that 2 by whatever our constant is now. Okay, so you can move the constant out in front of the limit. Okay, this one here, multiplication of functions, is the same as multiplying the limits. Same thing as this relationship here. Division is the same thing as dividing the limits, but g can't be 0, obviously. Okay, so if you have a function to an exponent, you can take the limit of that function, the whole thing, to the exponent. And then same thing for square rooting it. If you have a square root of function, you can square root that whole limit. Okay, so it's pretty interchangeable with saying your limits you can move around. Okay, and that can be helpful when you're trying to we're going to have to, it's hard to explain to you guys just without doing it, but trust me, you're going to want to know some of these things when it comes to getting rid of some of this stuff. Okay, so this one's pretty much what we just did in that last one. Limit as x approaches a of x is just a, because we would just plug a in, and that's the answer. Just like we just did in the last one. We had no restrictions. We can just plug the value in, and that's the solution. Limit of a of c is just a constant. So that's because there's no x. Like limit of 6 at 7, not 7x, just 7. Your answer is just going to be 7, because you can't touch the constant, right? The constant stays constant. Okay? So these last couple here, limit of x approaches a for x to the n is just a to the n, so you still put it in there. It keeps the exponent from where the x was. Simply putting a in for x there, and then same thing for the radical. Okay. Oh yeah, we're doing good. We're doing good. Might be able to do these two examples here. All right, let's stop. All right. Okay, so looking at this guy. So I kind of kept this solution on here already instead of me writing it out because, one, it's easier to see with that handwriting than mine, or type than my handwriting. And then this is just showing you how you can break them up. So limit of x goes to 5 of x squared plus 2x minus 3. So they broke it up into limit of x goes to 5 of x squared plus limit of x goes to 5 of 2x minus limit of x goes to 5 of 3. It's just proving to you that the properties work. This is kind of redundant, right? You guys, we could plug it in the beginning, right? And been fine. But it's showing you if you did break it up, you'd still be fine. We just did this one already. We did 32. Okay, so it's showing the properties and how they hold their value in terms of working. Okay. All right. This one. So evaluate using properties of limits. So what would you do for A? You just plug one in. There's no problem plugging one in, right? Okay. So it wants you to use the properties, though. So it does want you to go ahead and kind of do it out a bit. So we'll just kind of entertain it real quick. So it's going to be limit as x goes to 1 of x to the 4th minus limit x goes to 1 of 5x squared plus limit x goes to 1 of 1 all over limit, this is tedious, I know, of x plus of 2. Okay, probably wishing I put that solution on there too, huh? Okay, they're all limits, x goes to 1, and then I just sub these in here. Okay, so this right here, that's going to be 1 to the 4th. Right there, that's going to be minus 5, because 5 times 1 squared. Constant stays the constant. That's your top. Your bottom, 1 plus 2. Okay, so 1 minus 5 is negative 4, plus 1 is negative 3. Negative 3 over 3, we get negative 1 is the limit as x approaches 1. Okay, so this one, all they did was they went square root. They put all the stuff in the square root. So they did that. So at this point, we can plug these in. 3 squared is 9 plus 3. You get root 12. And if you remember your math 20, you can break that down. So 2 root 3 would be the limit of the part B there as x approaches 3. All right, so let's get to this next red box here, and then we'll do the last 4 examples tomorrow. Okay, so has everybody got that good enough? Yeah.
So in that equation, like that, you solve for L, right?
Correct. These are all limit. Yeah, the limit. Yeah, correct. The limit is 2/3. Okay. All right, so similar direct substitution provides the correct answer in example 3b. So we talked about if you just plug it straight in, you're going to get the same thing. 3 squared plus 3 is 12. Functions with this property are continuous at a. Now, it's an important topic. It's kind of what Emily was asking about earlier, which was that open dot. If you do that direct substitution, remember the one that canceled? the x minus 3, that one canceled, right? So when I plugged that one in directly, it didn't work. But what happens if I canceled it? So the x minus 3's go away. What would I have got? Because it was x minus 1 up there. What's 3 minus 1? Right, it's 2, and it was 1 over that. So that's the 1/2. Okay? So if you do simplify and plug in, you can find the limit, and that's what you're going to have to get really good at. But what I'm telling you is, if you plug in right away, it doesn't work, doesn't mean it doesn't always not work. It just means it's discontinuous there. Okay? So if you plug the value in right away and you don't have any luck, that means it's discontinuous at that point. That does not mean it does not have a limit. Okay? All right, so that's what this is saying here. I won't read the rest to you. That's what it's saying. And this last piece here I'll get to. So any polynomial that's continuous at a number, that means that when you plug in a, you get p of a, and it's no problem. Okay, any rational functions, p over qx, where p and q are polynomials, are continuous at every number such that q does not become 0. So that's when we get stuff on the bottom that cancels. So these are the two situations where you can expect continuous results. Okay, we won't get continuous results if our a causes a 0 on the bottom or has something that we can't calculate in terms of plugging it in right away. So, for instance, we can rework the solution to example 2 as follows, and we would get the same thing of 32, because it's continuous at 5. We have no problems. It's continuous there. Okay, we will stop there.